Good afternoon, students. Today we are going to start a new unit, that is balancing of rotating masses. Then, what is balancing of rotating masses and why we are going for balancing of rotating masses? That is, what is balancing means the high speed of engines and other machines, which is a common phenomena nowadays. It is therefore very essential that all rotating and reciprocating parts should be completely balanced as far as possible. If these parts are not properly balanced, the dynamic forces are set up. These forces may not only increase the loads on the bearings and stresses in the various members, but also produces the unpleasant and even dangerous vibrations. Now we are going to discuss the balancing of unbalanced forces caused by rotating masses in order to minimize the pressure on the main bearings when an engine is running. Then why we need to go for balance means due to the unbalancing of forces which are all produced in the rotating or reciprocating machinery due to the inertia forces which are associated with the masses. Balancing is the process of designing or modifying the machinery so that the unbalanced force is reduced to an accepted level, and if possible it may be eliminated entirely. Let us consider a particle or a mass moving in a circular path which experiences a centripetal acceleration and a force is required to produce it. An equal and opposite force acting radially outwards which acts on the axis of the rotation, and it is known it as a centrifugal force. This is a disturbing force on the axis of rotation and the magnitude of which is constant, but the direction changes with the rotation of the masses. The, in a revolving rotor, the centrifugal forces remains balanced as long as the center of the mass of the rotor will be lies on the axis of the shaft. When the center of the mass doesn't lies on the axis or there is an eccentricity, an unbalanced force is to be produced, where the centrifugal force is m omega square r. So these of the force which are all rotating at the axis of the rotation, and these are all to be balanced. Why balancing is necessary? As we discussed now, due to the high speed of the engines and all the rotating and reciprocating parts should be completely balanced in order to maintain a dangerous vibrations, and these are all to be properly balanced and dynamic forces are to be set up. The balancing of rotating masses, whenever a certain mass is attached to the rotating shaft, it exerted some centrifugal force whose effect is to be bend the shaft and it is produced vibration in it. In order to prevent the effect of centrifugal force, another mass is to be attached to the opposite side of the shaft at such a position so as to balance the effect of centrifugal force of the first mass. This is done in such a way that the centrifugal forces of both the masses are made to be equal and opposite. The process of providing the second mass in order to counteract the effect of centrifugal force of the first mass that is called a balancing of rotating masses. Here, these are the following cases are important from the subject, that balancing of single rotating mass by a single mass of rotating in the same plane. That is, in the same plane we are rotating, or we are creating the against to the previous or first object in a same plane, and the balancing of single rotating mass by two masses which are rotating in different masses. So for balancing of single mass, we are keeping the two masses at different planes. And the third stage is balancing of different masses rotating in the same plane, and balancing of different masses rotating in the different planes. Okay, let us go for these cases in detail so as to explain it clearly. This is the first case, balancing of a single rotating mass by a single mass rotating in the same plane. So in the same plane, the two masses are rotating. Consider a disturbing mass m1 which is attached to the shaft rotating at omega radians per second, which is showing in the diagram itself. Let us R1 be the radius of rotation of the mass m1, that is the distance between the axis of the rotation of the shaft and the center of gravity of the mass m1. We know that the centrifugal force which is exerted by the mass m1 on the shaft is Fc1, that is the centrifugal force exerted by the first mass, that is m1. So Fc is equals to m omega square r. Here the case, the first mass means Fc1 is equals to m1 omega square r1. This centrifugal force acting radially outwards and thus produces the bending moment on the same shaft. In order to counteract the effect of this centrifugal force or avoid the bending of a shaft, a balancing mass, that is m2 second mass, is to be attached in the same plane of the rotation so as that of the disturbing mass, such that the centrifugal forces due to the two masses are equal and which are in opposite direction. So based on the diagram we can see that the balancing mass and the axis of the rotation is same. Now what is the value of the centrifugal force which is to be acting counteract? That is, let R2 be the radius of rotation of the balancing mass for the mass m2, that is the distance between this axis of the rotation of the shaft and the center of gravity of the mass 2. Therefore, the centrifugal force due to the mass 2 equal to Fc2 equal to m2 omega square r2. Since why can't we place up the omega, that is angular velocity? The angular velocity of the first ball is rotating with a speed that should be same for the opposite mass also, since these two are connected with the same axis of rotation. So that's why the two masses which are acting same masses or may not be the same masses. So for that the angular speed for the both the masses may be equal. By equating, that's why the omega or the speed will be same for the both the masses. So by equating equation 1 and 2, m1 omega square r1 equal to m2 omega square r2, or simply by cancelling the angular velocities, m1 r1 is equals to m2 r2. For a note of that, the product M2 R2 may be split up into a convenient way, but the radius of rotation of the balancing mass M2 is generally made large in order to reduce the balancing mass M2. The centrifugal forces are proportional to the product of mass and the radius of rotation of respective masses because the omega square is all same for each masses. Then balancing of single rotating masses by two masses which are rotating in the different plane. We have discussed in the previous content that by introducing a single balancing mass in the same plane of rotation as that of disturbing mass, the centrifugal forces are to be balanced. In other words, the two forces are equal in magnitude and opposite in direction. But this type of arrangement for balancing will give rise to the couple which tends to rock the shaft in its bearing. Therefore, it is an order to put the system in complete balance. The two balancing masses are placed in the two different planes of rotation of the disturbing mass in such a way that they satisfy the following two conditions. One is static balancing and dynamic balancing. The net dynamic force acting on the shaft is equal to 0. This requires that line of action of the three centrifugal forces must be the same. In other words, the center of the masses of the system must lies on the axis of rotation. This condition for static balance. The net couple due to dynamic forces which are acting on the shaft is equal to 0. In other words, the algorithm of algebraic sum of the moments about any point in the plane must be 0. If these two conditions are together, will give the dynamic balancing. For that, there is a two possibilities may arise while attaching the two balancing masses. One is the plane of disturbing mass may be in between the planes of the two balancing masses, and second one is the plane of disturbing mass may lies on the left or right of the two planes containing the balanced masses. So let us go to the topic for the planes of disturbing mass lies in between the two balancing masses. Consider a disturbing mass M which is lying on a plane to be balanced by two rotating masses M1 and M2 which are lying in two different planes L and M. If you see in the diagram, the L and M are the different planes and the rotating mass M which is to be kept in between these two L and M. Let R1, R2 be the radii of rotation of the masses which are kept in the L and M respectively, and R be the radii of rotation of the balancing masses. Let L1 and L2 be the distances between the planes A and L and M, and L is equals to the distance between the two different planes L and M. So the total length between the L and M is the L, and the M is kept in a axis of the plane, that is capital A, and the distance between A and L plane is L1, and A and M plane is L2. So the total weight of the mass M is to be balanced by the two corresponding masses as M1 and M2. So let us consider the diagram of this is that the balancing of single rotating mass by two rotating masses in different planes when the plane of single rotating mass is lies between the plane of two balancing mass. We know that the centrifugal force exerted by the mass M in the plane A is M omega square R. Similarly, the centrifugal force exerted by the mass M1 in the plane L is Fc1 equal to M1 omega square R1, and the centrifugal force exerted by the mass M2 in the plane M is Fc2 is equals to M2 omega square R2. But since the net force is acting on the shaft must be equal to 0, this is to be satisfied for any balancing. So the net force acting on the shaft must be 0. So the force or the centrifugal force acting on the disturbing mass must be equal to sum of the centrifugal forces on the balancing masses. So Fc is equals to Fc1 plus Fc2. We know that Fc as M omega square R equal to M1 omega square R1 plus M2 omega square R2. By equating omega squares on both the sides, Mr is equals to M1 R1 plus M2 R2. Now, in order to find out the balancing force magnitude in the plane L, or the dynamic force at the bearing of the shaft Q, we are taking the moments about P. By taking the moments about P, which is the point of intersection of the plane M and the axis of rotation. So therefore Fc2 into L equal to Fc into L2, or M1 R1 L equal to MRL2. So M1 R1 we can write it as M1 R1 is equals to MRL2 by L. This is the third equation. This is the second equation. Similarly, for finding the balancing force in the plane M, or dynamic force at the bearing P, we have to take up the moments about Q, which is the point of intersection of the plane L and the axis of rotation. Therefore, Fc2 into L equal to Fc into L1, or M2 omega square R2 into L equal to M omega square R into L1. That is M2 R to L is equals to MR L1. By finally we get it that M2 R2 is equals to MR into L1 by L. It may be noted that the equation 1, that is MR equal to M1 R1 plus M2 R2, will represents the condition for static balancing. But in order to achieve the dynamic balancing, the equation 2 and 3 must be satisfied. That is M1 R1 and M2 R2 both are to be satisfied. Okay, then go to the second condition, that when the plane of disturbing mass is lies on one end of the plane of the balancing masses, that is either by keeping it in the left hand side or in the right hand side. So in this case the mass m is lies in the plane A, and the balancing masses is lies on the planes L and M, which is showing in the figure. The following conditions will be satisfied in order for balancing the system. That is, based on the diagram, we can say that Fc plus Fc2 equal to Fc1. So let us consider this is the axis of rotation above and below. That is the A or the A plane and M plane. For these two, the masses are acting in the upward direction, and for the plane L, the mass is kept in the downward direction. So for balancing, if you see in the right side diagram, the M and M2 are to be combined, and these are balanced by a single mass M1. Even though we need to balance the disturbing mass, that is M, with the balanced masses, so we can choose up the option called in between, keeping the balancing masses, or keeping the disturbing mass in between the balancing masses, or keeping the disturbing mass on one side of the plane of balancing masses. So this is the balancing mass kept at one side of the disturbing mass. So with that, m omega square r plus m2 omega square r2 is equals to m1 omega square r1. That is mr plus m2 r2 is equals to m1 r1. This is the fourth equation. Now to find the balancing force in the plane L, or the dynamic force at the bearing Q of the shaft, take moments about P, which is the point of intersection of the plane M and the axis of rotation. With that, Fc1 into L is equals to Fc into L2, or m1 omega square r1 into L is equals to m omega square r into L2. Finally, m1 r1 is equals to mr L2 by L. As it is the same equation we found in the disturbing mass is kept in between the balancing masses, that is the equation number 2. Similarly, to find the balancing force in the plane M, or the balance dynamic force at the bearing P of the shaft, by taking the moments about Q, which is the point of intersection of the plane L and the axis of rotation. Therefore, the Fc2 into L is equals to Fc into L1, or m2 omegas m2 omega square r2 into L is equals to m omega square r into L1. That is m2 r2 into L is equals to mr L1, or m2 r2 is equals to mr into L1 by L, which is the same equation we have founded in the third one. That is then for the next case, balancing of several masses rotating in the same plane. Consider any number of masses. Let us consider it is a 4 of magnitudes m1, m2, m3, m4 at a distance of r1, r2, r3, r4 from the axis of rotation of the shaft, and these are placed at the certain angles theta 1, theta 2, theta 3 and theta 4 with respect to the horizontal line axis, that is OX. By arranging these masses according to the position of R1 with respect to the angles, the diagram will be shown like this. We call it them as space diagram. Let these masses rotate about the axis through O and perpendicular to the plane of paper with a constant angular velocity of omega radians per second. The magnitude and position of the balancing masses may be found with analytically or graphically. So the resultant mass which are constructed here with two diagrams, one is space diagrams based on the position of considering them and with vector diagram. So the vector diagram will reveal the position of the thing. Then let us solve the magnitude and directions of balancing masses by analytically. First of all, we need to find out the centrifugal forces for individual masses, for individual rotating masses. We know the formula for the centrifugal force, that is m omega square r. Omega is the angular velocity. It is always be the same for all the masses. So we have to kept it aside and we need to find out the centrifugal force by the product of mass and the radius of rotation. So therefore finally we get it the centrifugal force formula as m r. That is a simple form. Then take up the resolving the centrifugal forces horizontally and vertically and find their sums. Firstly, we need to get it the centrifugal forces, and after that finding the centrifugal forces which are under horizontal condition and vertical conditions. With that, by amalgam, all algebraic sum of the horizontal and vertical forces, we have to kept these two in a separate manner. So from the diagram, we can see that OX be the horizontal line. With respect to that, the M1, M2, M3, M4 are the four different masses are positioned with respect to an angular theta 1, theta 2, theta 3, theta 4 about the OX, and the radius of rotations or the distances with respect to the horizontal line OX is of distance, that is R1, R2, R3, R4. Based on these diagram, the centrifugal forces are also be calculated. Finally, the sum of the horizontal components of the centrifugal forces, that is sigma h is equals to, for all the masses, here we are having the four masses. So for all the masses, we need to calculate the horizontal components of CF. The CF values is sigma h is equals to m1 r1 cos theta 1, m2 r2 cos theta 2, and so on, m4 r4 theta 4, that is cos theta 4. And Also, the sum of the vertical components of the centrifugal forces has sigma p is equals to m1 r1 sin theta 1, m2 r2 sin theta 2, and so on, m4 r4 sin theta 4. By calculating the third step is by calculating the magnitudes of the resultant centrifugal force. The magnitude of centrifugal force resultant is Fc is equals to square root of sigma h square plus sigma v square. So if the theta is the angle when the resultant force makes with the horizontal, then the resultant angle will be tan theta to theta is equals to sigma v by sigma h. The balancing force is then equivalent to the resultant force, but we need to kept in opposite direction. Now finding the magnitude of balancing force in such that Fc is equals to mr, that is balancing mass and its radius of rotation. So the same technique what we have applied here, it is a analytical method. With the graphical method, the magnitude and the position of balancing masses may also be obtained. That the firstly we need to draw the space diagram with the position of several masses which are all under the diagram of basic. So this is a space diagram. Nextly, find out the centrifugal forces, that is product of mass into radius of rotation which is exerted by the each mass. Now draw the vector diagram with all the possible centrifugal forces such that in the diagram will represent small ab the centrifugal force which is exerted by the mass m1, which is in the magnitude and the direction, so that with some suitable scale. Similarly, draw the centrifugal forces which are exerted by the remaining masses, that is m2, m3, m4, for values of m2 r2, m3 r3, and m4 r4 by a line BC, CD, and DE to represent the centrifugal forces with some suitable scales. Now, finally, as a polygon of losses, the closing side, that is AE, will represent the resultant force in magnitude and direction. So the figure B, it is the vector diagram for representing of analytical and graphical. Which one is the easier means the graphical technique is the easiest one. So after solving either by graphically or analytically, the solution of the balancing mass either in magnitude and direction both will be of same. So here no need to calculate the each and every direction or the angles. So by simply placing or drawing the parallel lines of the existing space diagram, and you just forward the parallel lines to the vector diagram in the connectivity. Now finally the balancing mass is then equal to the resultant force, but these are in opposite directions, so that the final balancing mass magnitude is mr. Then let us consider today's class. For the overview is that what is static balancing and what is dynamic balancing. For what we are going to balance the rotating masses. These are the topics we have covered in the today's class. And what is the possible ways of balancing the rotating masses? One is balancing of single rotating mass by single mass rotating in the same plane, and balancing of single rotating mass by two masses rotating in the same different planes. These two contents are solved in the today's class. In the next class, we will do the problems also.